During this PowerPoint, we are going to discuss the structure of the Earth and plate tectonics. The interior of the Earth is divided into layers based on chemical and physical properties. The Earth has an outer silica-rich, solid crust, a highly viscous mantle, and a core comprising a liquid outer core that is much less viscous than the mantle, and a solid inner core. Working from the center of the Earth out, we have the inner core is a primarily solid sphere about 1,220 kilometers in radius, situated at Earth's center. Based on the abundance of chemical elements in the solar system, their physical properties, and other chemical constraints regarding the remainder of Earth's volume, the inner core is believed to be composed primarily of a nickel-iron alloy with a small amount of some unknown elements. The temperature is estimated at 5,000 to 6,000 degrees Celsius. The liquid outer core is 2,300 kilometers thick and, like the inner core, composed of nickel-iron alloy, but with less iron than the solid inner core. The mantle is approximately 2,900 kilometers thick and comprises 70% of the Earth's volume. The core makes up 30% of the Earth's volume, with the outer crust, where we live, less than 1%. In the mantle, temperatures range from 500 to 900 degrees Celsius at the upper boundary, with the crust to over 4,000 degrees Celsius at the boundary with the core. We shall see that this process is very important for plate tectonic motion. The outermost layer is the crust. This is the most familiar to us, as it is where we live. The distinction between the crust and mantle is based on chemistry, rock types, and seismic characteristics. The Earth has two different types of crust: continental crust and oceanic crust. Each has different properties and therefore behaves in different ways. Continental crust. Continental crust forms the land, the continent, as the name suggests, that we see today. Continental crust averages about 35 kilometers thick. Under some mountain chains, crustal thickness is approximately twice that thickness, about 70 kilometers thick. The mountains we see on Earth have deep roots in the crust that we can't see. The crust floats on the more dense mantle, like how only the tip of an iceberg sticks out of the water. We see only the tip of the continental crust, the mountain ranges. Continental crust is less dense and therefore more buoyant than oceanic crust. Continental crust contains some of the oldest rocks on Earth. Ancient rocks exceeding 3.5 billion years in age are found on all Earth's continents. Oceanic crust. As the name already suggests, this crust is below the oceans. Compared to continental crust, oceanic crust is thin, 6 to 11 kilometers. It is more dense than continental crust, and therefore, when the two types of crust meet, oceanic crust will sink underneath continental crust. The rocks of the oceanic crust are very young compared with most of the rocks of the continental crust. They are not older than 200 million years. If we can't go to the center of the Earth, except in fictional movies, how do we know what the internal structure of the Earth is like? We need to use geophysical imaging techniques to model what is going on below our feet. For example, when there is an earthquake, it sends seismic waves through the Earth. Seismologists can measure the time it takes for these waves to reach seismic monitoring stations set up around the globe. The different layers in the Earth have been inferred using the time of travel of refracted and reflected seismic waves created by earthquakes. Other geophysical methods, for example measuring different gravity, magnetic, and electrical anomalies by air and/or satellite, can help to reconstruct shallow crustal features. We can also go and examine rocks at and near the surface of the crust through field work, drilling boreholes, and mining. What is plate tectonics? If you look at a map of the world, you may notice that some of the continents fit together like pieces of a puzzle. The shape of Africa and South America are a good example. This is because they did used to fit together. The Earth as we see it today was not always like it is now. Land masses have pulled apart and joined together by the process we call plate tectonics. There are 12 major plates on Earth, each of which slide around at a rate of centimeters per year, pulling away from, scraping against, or crashing into each other. Each type of interaction produces a characteristic tectonic feature, like mountain ranges, volcanoes, and/or rift valleys that we will discuss on the following slides. This diagram shows the major tectonic plates. America lies on the North American plate. Also, the plate boundary between Africa and South America. Look how the coastlines in these countries match up very closely. Plates are made of rigid lithosphere, formed at the crust and the extreme upper mantle. The asthenosphere beneath the lithosphere is part of the upper mantle and is so hot that it is 1 to 5% liquid. This liquid, usually at the junction of the crystals, allows it to flow, which is why astheno means weak. Beneath the asthenosphere is the rest of the mantle, which is completely solid, but can also flow on geological timescales because of the intense temperatures and pressures involved. The base of the lithosphere and asthenosphere boundary corresponds approximately to the depth of the melting temperature in the mantle. How and why do tectonic plates move around? The question of how tectonic plates are moved around the globe is answered by understanding mantle convection cells. In the mantle, hot material rises towards the lithosphere, like hot air rising out of an open oven. Ever opened an oven door and felt the blast of hot air coming past your face? The hot material reaches the base of the lithosphere, where it cools, and sinks back down through the mantle. The cool material is replaced by more hot material, and so on, forming a large convection cell, as pictured in the diagram. This slow but continuous movement in the mantle causes the rigid tectonic plates to float around the Earth's surface at an equally slow rate. We are now going to discuss the processes that occur at plate tectonic boundaries. What happens when plates meet? Firstly, there are 3 types of plate boundaries, each related to the movement seen along the boundary. Divergent boundaries are where plates move away from each other. Convergent boundaries are where plates move towards each other. Transform boundaries are where plates slide past each other. See diagrams for each. It is important to remember the names of the boundary types and the motion involved. In plate tectonics, a divergent boundary is a linear feature that exists between 2 tectonic plates that are moving away from each other. These areas can form in the middle of continents or on the ocean floor. As the plates pull apart, hot molten material can rise up this newly formed pathway to the surface, causing volcanic activity. Look at the diagram. Mantle convection cells causes the plates to break apart, and also as a source for new molten material. Where a divergent boundary forms on a continent, it is called a rift, or a continental rift. An example would be the African Rift Valley. Where a divergent boundary forms under the ocean, it is called an ocean ridge. Ocean ridges. This map shows the age of the oceanic crust. The red coloring shows the youngest ages, while the dark blue shows the oldest ages, around 200 million years old. Where are the ocean ridges located? Where are the divergent boundaries? The divergent boundaries are where the plates are pulling apart and new material is being produced. Therefore, the ocean ridges are in the middle of the red areas. The boundaries are in fact shown on the map. We can see a progression of the oceanic crust getting older away from the ocean ridges, like a conveyor belt. Iceland is located right on top of a divergent boundary. In fact, the island exists because of this feature. As the North American and Eurasian plates were pulled apart, volcanic activity occurred along the cracks. With many eruptions over time, the island grew out of the sea. Why don't we have islands like Iceland wherever we get an ocean ridge? Scientists believe that there is a large mantle plume, an upwelling of hot mantle material located right underneath where Iceland was formed. This would mean that more material would be erupted in the Iceland area compared with if there was just the divergent boundary without the plume underneath it. Convergent boundaries are where the plates move toward each other. There are 3 types of convergent boundary, each defined by what type of crust, continental or oceanic, is coming together. Therefore, we can have continent-to-continent collision, continent to oceanic crust collision, or ocean-ocean collision. When continental crust pushes against continental crust, both sides of the convergent boundary have the same properties. Think back to the description of continental crust, thick and buoyant. Neither side of the boundary wants to sink underneath the other side, and as a result, the 2 plates push against each other and the crust buckles and cracks, pushing up and down into the mantle. High mountain ranges, for example, the European Alps, the Himalayas, formed this way. Example: India used to be an island, but about 15 million years ago it crashed into Asia. Look at the map. As continental crust was pushing against continental crust, the Himalayan mountain belt was pushed up. Mountains were also pushed down into the mantle, as the normally 35-kilometer thick crust is approximately 70 kilometers thick in this region. Mount Everest is the highest altitude mountain on the planet, standing at 8,840 meters high. This means that below the surface, at the foot of the mountain, the crust is a further 61 kilometers deep. At a convergent boundary, where continental crust pushes against oceanic crust, the oceanic crust, which is thinner and more dense than the continental crust, sinks below the continental crust. This is called a subduction zone. The oceanic crust descends into the mantle at a rate of centimeters per year. This oceanic crust is called the subduction slab. When the subduction slab reaches a depth of around 100 kilometers, it dehydrates and releases water into the overlaying mantle wedges. The addition of water into the mantle wedge changes the melting point of the molten material, there forming new melt, which rises up into the overlaying continental crust, forming volcanoes. Subduction is a way of recycling the oceanic crust. Eventually, the subduction slab sinks down into the mantle to be recycled. It is for this reason that the oceanic crust is much younger than the continental crust, which is not recycled. The Andes mountain range along the western edge of the South American continent is an example of a mountain belt formed by subduction. The continental crust of the South American plate has buckled under the compressional strain of converging with the Nazca and Antarctic plates. Additionally, there are many volcanoes, the result of melting of the subduction slab and the production of new material that has risen through the crust to the surface. When 2 oceanic plates converge, because they are dense, one runs over the top of the other, causing it to sink into the mantle, and a subduction zone is formed. The subducting plate is bent down into the mantle to form a deep depression in the seafloor, called a trench. Trenches are the deepest parts of the ocean and remain largely unexplored. Manned or unmanned submersible vehicles have explored small parts of trenches, discovering new species, like the fish photographed here, and amazing ecosystems. The third type of boundary are transform boundaries, along which plates slide past each other. The San Andreas Fault, adjacent to which the city of San Francisco is built, is an example of a transform boundary between the Pacific Plate and the North American Plate. This map summarizes all the known plate boundaries on Earth, showing whether they are divergent, convergent, or transform boundaries. What's the connection between volcanoes and plate tectonics? This map shows the margin of the Pacific tectonic plate and surrounding region. The red dots show the location of active volcanism. Notice how the majority of the volcanism is focused in lines along the plate boundary. For this region, this area is known as the Pacific Ring of Fire. But why are all the volcanoes located at the plate margins? Volcanoes are formed in 3 ways. Via subduction, the subducting slab dehydrates to form new melt that will rise through the crust to be erupted at the surface. Via rifting, when 2 plates pull apart, magma rises, producing volcanic eruptions at the surface. At hotspots. Hotspots do not necessarily occur along a plate boundary, so hotspot volcanoes can form in the middle of a tectonic plate. Hotspot volcanoes in the middle of the Pacific Plate. Can anyone guess where they are? Hawaii. Firstly, what are hotspot volcanoes and how do they form? A hotspot is a location on the Earth's surface that has experienced active volcanism for a long period of time. The source of this volcanism is a mantle plume of hot mantle material rising up from near the core mantle boundary through the crust to the surface. A mantle plume may rise at any location in the mantle, and this is why hotspot volcanoes are independent from tectonic plate boundaries. The Hawaiian island chain are an example of hot spot volcanoes. Hotspots commonly form volcanic island chains, like the Hawaiian Islands. These result from the slow movement of a tectonic plate over a fixed hotspot. Persistent volcanic activity at a hotspot will create new islands as the plate moves the position of the old volcanic island from over the hotspot. Therefore, at one end of the island chain, you see the youngest, most active volcanic island directly over the hotspot, and along the island chain, the extinct volcanoes become older and more eroded. This is why geologists can use hotspot volcano chains to track the movement of the tectonic plate through time. We have seen the connection between volcanoes and plate tectonics. Is there a connection between earthquakes and plate tectonics? The black dots on this map of the world depict where earthquake activity is occurring. You can see that, as with volcanoes, the earthquakes are not randomly distributed around the globe. Instead, they occur in linear patterns associated with plate boundaries. Note, this diagram of earthquake distribution closely resembles the Pacific Ring of Fire distribution of volcanism. We know there are 3 types of plate boundaries: divergent, convergent, and transform. Movement and slipping along each of these types of boundaries can form an earthquake. Depending on the type of movement, the earthquakes occur in either a shallow or deep level in the crust. The majority of tectonic earthquakes originate at depths not exceeding tens of kilometers. In subduction zones, where old and cold oceanic crust descends beneath another tectonic plate, deep focus earthquakes may occur at much greater depths, up to 700 kilometers. These earthquakes occur at a depth at which the subduction crust should no longer be brittle. Due to the high temperature and pressure, a possible mechanism for generation of deep focus earthquakes is faulting. Earthquakes may also occur in volcanic regions and are caused there both by tectonic faults and by the movement of magma, hot, molten rock, within the volcano. Such earthquakes can be an early warning of a volcanic eruption. Plate tectonics summary. The Earth is made up of 3 main layers: core, mantle, crust. On the surface of the Earth are tectonic plates that slowly move around the globe. Plates are made of crust and upper mantle, lithosphere. There are two types of plates. There are three types of plate boundaries. Volcanoes and earthquakes are closely linked to the margins of the tectonic plate.